Good morning, thanks very much. It's really good to be here. Okay, I've got quite a lot of material, so I'm going to go quite fast and hopefully I'll get it in time. Right, start at the beginning. Just to talk about a little bit of theory. Very simple land use model. Basically what we're talking about a series of time steps, T0 to Tn, and we're looking to establish these key things. How much land use is changing, where is it changing, and how is it changing? So cellular automata. Why cellular automata? Well, basically this is something that arose out of the Manhattan project at Los Alamos in New Mexico in the late 40s and 50s, with these guys here, Stanislav Ulam in particular on the left and John von Neumann on the right. And this is basically Ulam's definition of cellular automata. Given an infinite lattice or graph of points, each with a finite number of connections to certain of its neighbours, each point is capable of a finite number of states. The states of neighbours at time Tn induce in a specified manner the state of the point at time Tn plus 1. This rule of transition is fixed deterministically, or more generally may involve partly random decisions. So there's a lot of talk in the modelling literature, the land use modelling literature, about transition rules and states and neighbours, and all of it comes back to this. Well, then there were some sort of experiments by mathematicians in later on, like John Conway, who came out with a game of life, which I'm sure you've seen if you know anything about cellular automata. It's a kind of classic example. As far as actually applying these definitions to geography, we've got this guy on the right here, Waldo Toller, looking very relaxed in his retirement there in Santa Barbara in California. And he basically said, well, yeah, we're talking about a cell. A cell could be a grid, it could be a map, and we could, our cells could contain land uses. And I think probably the best known application of cellular automata is probably this by Roger White and Guy Engelin, about 20 years old now, and applied inside a major standalone commercial software. So how does this model of Engelin and White actually work? Okay, well basically you start with your initial land use map, which in the case I'm going to talk about today is 1956. You establish your neighbourhood rules. You have a stochastic element, this randomness that Ulam was talking about. You have accessibility, which is usually your distance to roads or your infrastructure networks. Suitability, so the background carrying capacity of the background land to support a land use. You don't get cereal crops on mountain tops. Urban areas you don't build houses on cliff faces generally. And then you have your zoning, which could be your management, your land planning, so protected areas. And you calculate transition potential. And this transition potential is what allows you to calculate your new map at your next time step. Okay? And the first thing we do is, on a process we call calibration, we simulate our next land use map that we've got available, which in my case was 1999, so quite a long time step. And it's pretty simple. It's a pretty straightforward model. So I'll just to talk about the neighbourhood dynamics. Okay, at the core of this model by White and Engelin, we have the idea that there's the susceptibility of an individual cell C to change state at time Tn is a function of the influence of the cells in its neighbourhood. Okay, so we can make some observations. So when you do a land use change analysis, which is normally your starting point for this type of modelling, you see there's some changes that you frequently repeat themselves. So you don't get irrigated land that just turns up out of nowhere. Normally it's farmland that was not under irrigation. Yeah. Okay, and we could say that's attraction. That could be represented in our model as attraction in the cell neighbourhood. Some land uses are always separate. So generally you find mining areas separate from urban land. That's not always the case, but as a general rule, I think we can say that. And this would be repulsion. And then you have some changes that never happen. Urban land changing into conifer forest. Very, very rare situations this might happen. As a general rule, it doesn't tend to. And this is an example of persistence. Some things nearly always stay where they are. And that's urban land is a good example of this. Well, this is the cell neighbourhood and the influence table. Basically here we've got our distances, 0 to 200, quite a small neighbourhood, and we've got the attractiveness of urban to these other classes. And in particular, I've highlighted in orange urban because I'm only going to talk about urban today in our model. So this is the attraction of urban to urban. And in order that in the second time step you get urban land where urban land was before, it needs to have a high value at 0 on the cell itself. If you don't have a high value at 0, your urban land gets up and it walks across the map, which you don't want. Okay, so in R, this is just, we generate a matrix. That's our cell neighbourhood, and this is our command in R. Stochasticity, right? Well, this is Ulam's, again, these partly random decisions. Well, human activity in the landscape, we know it's not completely deterministic. Some things, either they're random or we've got so many unknown causes that effectively we have a kind of randomness. How do we do it? Well, we actually make some parts of the simulated landscape more attractive at random. But we don't want much randomness, because in general we're saying that human activity is more deterministic than random. But okay, so we don't want to go overboard. Accessibility again. Well, this is again fairly simple equation from Roger White's work in the 90s. We take our raster a simple distance map from road networks, which you could calculate in R or in another GIS, and we reclassify it just to give higher values to cells with closer distances. Suitability, okay, this is what I was saying before, the intrinsic susceptibility of a cell to be occupied. So zoning, again, this is the institutional characteristics, so the planning restrictions and policies. Generally, these are stationary throughout the time steps. You could update them in an integrated model to feed in from some other information you had. So aridity due to climate change here, for example. In this example, I've not done any of that. It's stationary. What's the problem? Well, there's a really good CA land use modelling system on the market called Metronamica. It's quite expensive. It's standalone. I should say, first of all, it's very good, yeah, but it is expensive. It's standalone. If you want to do any GIS, you've got to go outside and do it in a different system. If you want to do your statistical goodness of fit testing, which becomes more and more important with the model. So people who are just interested in finding out about these models are shut out. And so also are stakeholders, so the people that you might want to work with, if you're talking about land planning, you might want to work with farmers or municipal authorities. And it's very difficult for them to access this model. You have to buy it as part of your project and then give them results. And this is kind of, I think, a little bit of an idea that we have from the 1990s that experts are going to come along and they're going to do policy support, and then they're going to roll out this information and planners are going to implement it. And I think this is a little bit of an outdated philosophy. Other problem is Windows only. There are some other non-commercial applications. They have some of these limitations as well, and there are some commercial applications that I don't think are true cellular automata, like the land change model in Idrisi. They talk about cellular automata, and then you actually find that it doesn't really respond to any of these definitions that you have from Stanislav Ulam. So anyway, that's debatable. I don't want to offend anyone, but I don't think they're real cellular automata. So we wanted something that gives you complete freedom to explore, that runs inside a widely used environment like R, and it responds to all these problems I was just talking about. And for me particularly, it was important because we work a lot with stakeholders. This is one of our workshops in Doñana, which is a natural area in the south of Spain. This is our website. So we're saying to them that, yes, everything's online. Go to the website. You can download everything, all the questionnaires, all the information. And at the end, we have to say everything. Except the land use model. Sorry, you can't have that. That's licensed software. And that's not good enough, I don't think. So, right, first of all, it's a prototype I'm going to present. I can't compete with all this professional development that's gone in. I'm only dealing with one land use at a time. There's no graphic interface, a lot of development. But anyway, I'm going to put the code online at this blog. It's not there yet, I've just set the blog up, so bear with me. Right, well, we've actually had quite a nice introduction to R anyway. Anyway, it's got a whole series of advantages, I think, for this. Ease of data handling for me is absolutely great. I mean, you can bring in a raster data, an ASCII file, you can take the values out, you can do a whole load of things to them, you can return them, and it doesn't screw it up. So it's really, really good, that. For this model I'm going to talk about, you don't need a very powerful computer. About a gig is probably enough of RAM, and any operating system that runs R, as far as I know, most of them do. You need the raster package, AOD, SP, and SDM tools, just for the spatial analysis. So you don't need a great deal of additional stuff. This is the model that I've actually built is based in this area. As I was saying, this is southwest Spain. This is a natural area called Doñana, and I'm going to show some examples of my land use simulations for the growth of this large town called Sanlúcar de Barrameda. So right, land use demand. You need to know how much land is changing. Remember, I'm only going to be talking about urban land. So this is a binary map. Urban land is 1, non-urban land is 0. And our land use demand in our second date, in our calibration map, is just simply how much land we know changed to urban in that date. So there, 1999, 4502. Okay. Right, how do we calculate it in R? There we go. Very simple, frequency command. There we can see we had 6,752 cells allocated to urban. That's a demand of 157 cells a year. So at each time step we need to locate 150 cells of urban land. Yeah. Okay, this is our matrix that we've just seen for our neighbourhood rules. And then we apply a focal moving window. Yeah. Using this command, the focal command, yeah, and this is the window that we saw before. Okay, it does some quite odd things here. I'm not quite sure why. It creates some holes in the map, so we can fill in these areas from the original map. That's something I should look into more, but haven't had the time. So here we are. Here's our neighbourhood filter applied, and we can see, well, basically the green area is where the city was in our first time step, and the areas in yellow and red are on the fringe of the city, and those are areas that have the second highest potential. So the highest potential for transition is in existing urban areas, because I say if you don't, your urban areas walk all over the map. The second highest potentials are going to be on the fringes. Yeah, so it's pretty straightforward. The randomness, right, well, sorry for this big slide of code. It's longer than it needs to be, because as you can see, I'm not an expert in R, and nor am I a programmer. But effectively, the Weibull distribution is a skewed distribution. So this means that we're not getting values consistently between 0 and 1 like we would in a normal distribution. We're getting values they tend towards 1. So most of our values are going to be 1. And that's really important because we're multiplying it into the transition potential equation. So most of the time, we're going to get determinism. But occasionally, we're going to get values that are not 1, and they can be quite a lot higher than 1. So this is how we've put our randomness in, and then we've made sure that we set the city to 1. So we're not actually randomising inside the urban area, because this doesn't really fit inside our conceptual model. You know, we believe that there's a possibility for urban areas to randomly occur outside of the existing city, but we don't really want chunks of our city to randomly disappear. Yeah. Anyway. Accessibility. Well, this really is very straightforward stuff. In GIS, this is just a reclassification. I mean, I suppose it's not very user-friendly, but it's not difficult either. You know, we've got a vector there, and we're saying that everything from minus infinity to 100 is given 1, everything from 100 to 300 is 0.9, and so on. So we've got a distance decay effect falling off with a halving distance of about 2.5 kilometres. Yeah, so it's half its effect at 2.5 kilometres away from a road. We can play around with these values. We apply the accessibility equation. There we go, and then we plot it out, and that's what we get. It's quite a good display, so we can see that there's actually some white areas inside the roads itself. And why is this, we wonder? Actually, this is because areas that are actually really close to the road, i.e. on the road, are infinitely high. And the colour scheme I've got doesn't actually plot infinite values. I don't know, can anything plot infinite values? Sort of philosophical question. So I need a better colour scheme there. Yeah. Right, the slope, this is our suitability. I've just chosen a slope map, which is the simplest, most typical example for locating urban land. Generally, urban land is found on slopes of less than about 5%. Most of this area is in fact less than about 5%. Blocked out in white, by the way, is the protected area. Come on to that in a second. So that's our suitability map. And zoning, well, you've got two ways to incorporate it. I chose the simplest, fastest way out, which is just to exclude the no data areas from the model. Or you could add it just in the same way that you did suitability, as another map with values from 0 to 1. But we've got to remember that if we're returning zeros, we're putting zeros into a multiplying equation, so our result will be 0. So again, we don't want the land use in that, we want it to stay the same, we don't want it to disappear. So we've got to have a little if condition in there. Haven't got around to that because, as I say, I took the easy way out. This is my pseudo code. Again, I repeat, I'm not a programmer. So one of the things you'll see here is I've got a loop within a loop. Hasn't actually seemed to create me too many problems, but I think there's definitely better ways to do this. And what we're doing is we're running the loop. Okay, so we're running the neighbourhood rules. We're creating our random map, then we're calculating our total transition potential just by multiplying these things together. We're extracting the values, and then we're entering a second loop to locate, this is for each time step, 157 cells of urban land. And how do we do this? Well, we take the maximum, using the max command, and we change it to -999. So the second time we go into that loop, so that we're not picking the same maximum. Okay? It's just a solution that seemed to work. Here's our total transition potential. You can see that we've got this speckle effect is because of our random map. So we've got a lot of values in cyan there, which are 1 or very close to 1. But then there's some areas which are outside the urban area which have higher potential. So anyway, yes. So what I've done here is I've done 3 simulations to test it. Okay. Got the first one is the one I've been talking about, I've been showing on the slides. In the second one, I've enhanced the randomness by changing the scale parameter here, which is the exponent of this. So instead of having it as a half, I've got 0.9. Then a third simulation, I've reduced the neighbourhood influence by a factor of 100, in fact. So this reduces the power of the neighbourhood respect to the other variables. Right. So this is what I'm trying to simulate. I've got a real map 1956, very little urban growth there, and then this kind of sprawling urban growth with some new irrigation channels. Actually, this is not just urban, this is sort of artificial surfaces here anyway. So we've got these irrigation channels in 1999, and I'll have a go at it. Well, that's the first one. Whew, it's not that good. I mean, it's not too bad. I've managed to grow some land. But we can improve it. So this is why I jacked up the randomness a little bit, and we can actually see that this has the effect. Let me see. It's going to have a think about this. If I can go back. Just thinking about it. There we go. You can actually see the difference between the first one and the second one. I haven't got any urban areas that just sort of spring up, but when I up the randomness, they start to spontaneously occur. And then when I reduce the effect of the neighbourhood respect to the other variables, I start to get a more realistic pattern. I say more realistic because this is very, very clumped, isn't it? But we're starting to see some sort of fraying at the edges, and this is possibly starting to be able to simulate a little bit this spread along the coast. So anyway, that was the best simulation I came up with. Well, it's more or less realistic. At least it looks like land use. I've seen a lot of simulations that look like, sort of mushrooms or algae blooms. This doesn't look like that. It seems to be growing step by step. There's some problems. We've got some good things. Some smaller urban patches do spring up spontaneously, which reflects reality to a certain extent. There's a bit of linear dispersion reflecting the influence of the accessibility. I need to take the irrigation channels out of this map, as you can see, because we don't grow new irrigation channels alongside existing ones. These are problems that can be solved. Right, and I hope I've got time to just quickly go into the statistical. 2 minutes, right, very quickly. Okay, I've used Kappa, which is a standard map comparison technique, and I haven't used unmodified Kappa because this causes some problems. It doesn't take into account areas of no change. So we've used this modified statistic from Van Vliet. This is programmed by a colleague of mine. I'm not going to show it to you because it's not ready yet, but anyway, it works, and we're going to package it up and make sure that it's available. How do we know it's any good? Well, higher than 0.1, usually you have to take my word for it, I'm afraid, but if you look at the literature, higher than 0.1, you're starting to be able to simulate growth effectively. Well, fractal dimension, this is a pattern comparison measure. In general, the closer between 1 and 2, the closer to 2, the more dispersed or the more sprawling, the more irregular the pattern. So we can see in our real maps, we've got quite a dispersed pattern, quite dispersed boundaries. In our simulations, not so dispersed. Remedy, more randomness, stronger accessibility perhaps to scatter those urban areas along the roads. And then what I've done is I've taken this and I've applied it to the real map in 2007 with the same growth tendency, 157 cells a year up to 2050. So there it is working. And that's almost the last slide. I'll just let that finish. Okay, right. Well, I'd like to put the full script up. I haven't done it yet, as I said. The real prize would be to add the capability to model multiple land uses. You just need to be able to sort. You would have each land use would have its own transition potential matrix, and you need to sort out which of those is the highest for each particular cell between the different land uses. Something we've done in Python, but we haven't done it in R yet. We're going to apply it. And this is just a tiny little bit of publicity, sorry about that, for our project, FP7 project, Complexity in Low Carbon Energy Systems, Climate Change and Land Use. So we're going to try and apply some of these techniques. And that's me. Please feel free to contact me. That's the end. Any questions?
Josh Allen. You talked about introducing randomness, but your final 2050 forecast didn't have any representation of uncertainty in the map. It was a deterministic forecast.
In what sense?
You only produced one map of, okay, it's a forecast, but it said this is what it will be in 2050, not there's a 50% chance that this will be Colin.
Oh, I see what you mean. Yeah.
Monte Carlo analysis or something along those lines to produce a probability rather than just a yes or no answer.
You're totally right. I mean, in no circumstance would I want to say this is what it'll be like in 2050. I suppose that's just an example I've given to show how you would run this forward into the future. But yeah, absolutely, you'd want to do a whole series of runs, hundreds, as many as you've got time for, and then put them together, absolutely, and give a nice probability. What are the probability of particular areas to change? I totally agree, yeah.
How long does the model take to run?
The model takes about 20 minutes on my laptop. So it's 43 years. It's not very fast, but neither is it so slow that it gives you a headache. I think if we start trying to introduce other land uses, we'd have to try and look at modifying the code. I think R offers the facility to escape a little bit from loops, but I'm not sure exactly how that works. But I'd be very happy if someone could tell me.
Any other questions for Richard?
Yeah.
I know you've only got 2 data points to start
Yeah.
with, but have you thought about using non-linear growth patterns?
You mean the demand would not be sort of a straight line, but rather well, you can do it. Yeah, I mean that would be interesting for your future. I suppose to simulate the future, you might want a series of scenarios in which the growth does a series of things. And I mean, that's definitely been the case in Spain. You know, we've had kind of years and years and years and years of consistent urban growth, and all of these models have been great. You know, business as usual, it's always the same, it just keeps on growing. And then suddenly we have the economic crisis in 2007, and that just throws everything out the window. So that's a clear kind of weakness in these models, I think.
Anybody else? Other questions? I was going to ask myself.
Yeah.
You've obviously got something going on with your irrigation channels.
Yes.
You could. How does it, or is there a way of incorporating the reverse effect that, say, someone builds a road,
Yeah.
and then you get development off of that?
Yes, I mean, you can, again, you could incorporate, I mean, I think it would be easy enough to introduce a new map at a particular time step that could have new road development. And as soon as that happens, that can then be calculated, and then you will get new things coming up off that new map.
Put a feeding into the looping somewhere.
Yeah, definitely. That would be really good, and that would improve it really. I think, because quite a lot of the model, the Metronamica model that we've used, the commercial version, is quite static in that sense, and it doesn't offer that flexibility. So, yeah.
Thank you very much. Sorry.
Can you compare the output of this to the commercial software in the same area?
Not for the same area, but I can. I just haven't had time. I can do, because I've got the same model and the same commercial software. Perhaps I should do that and put it on the blog. That would be interesting. In theory, it should be identical. If I put the same rules in, it should be identical. That would be the test, wouldn't it? So sorry, I haven't had time to do it.
Okay. In which case, thank you very much.
Yeah.